These are the first notes. This video covers the first notes for section 2.2, or what I'm referring to as day 1. Sometimes you'll see this referred to as 2.2.1, so just the first day. And we're going to cover density curves, and then we're going to talk about a very unique, very special density curve called the normal curve, or the normal distribution. It is probably one of the most important shapes or curves that we use this year. We will continue using it all year long. The normal distribution, normal curve, really plays an important part in the rest of this book. All right, so if we were in class, I would have asked everybody to come to class having measured their foot. So I think I say here your right foot. And then I would give everybody a Post-it note, and on that Post-it note you would write to the nearest 1/10 of a centimeter the length of your right foot. Seeing as how we're not actually in class and you're watching this online, I'll kind of talk through the example that we would have done in class and the resulting distribution that we would have gotten. All right, so what I do is I typically then give everybody a Post-it note, like I said, and have them go and put their foot length on the board. So I create this little axis, and then you can see this one on the right. I use different color Post-it notes for different classes. The one in blue, I just gave everybody the same color that year. So there's really no difference in the colors. What I've done then is I said, well, for this video, I needed to look at data, so I just combined these. So for the last 2 years, the foot lengths of all my AP statistics students, and they're listed here. All of the combined all the data from those 2 histograms and just made one histogram. All right, so you can see that this looks fairly symmetrical. I would certainly not call this skewed. It looks fairly symmetrical. And not only that, it sort of follows this very important curve that we call a normal curve. So this distribution sort of foot lengths tends to follow a fairly normal distribution where there's very few observations or foot lengths beyond, say, 32 or beyond 18 centimeters. All right, and so the histogram is a graphical representation of the distribution of foot lengths for my AP statistics students. We will often refer to this as a frequency distribution. It just will be more convenient to think of it as a continuous curve sometimes. It makes calculations easier. So if I ask, like what percent of the students have foot lengths less than 23 centimeters long? Well, that's 23 here. So we'd have to count all of these boxes, all of these Post-it notes, and that's tedious. But if instead I treat this distribution as though it's following this normal curve, the calculation is very quick to figure out what percent fall to the left of this line here at 23. All right, so here we want to talk about density curves, sort of some rules about density curves. Now, one of our density curves is called the normal curve, but density curves are useful so that we can look at areas rather than have to sit and count observations. So sometimes it's helpful to use a graphical model called a density curve to describe the location of an individual in the distribution. We can talk about what percent of the foot lengths are below your foot length or above your foot length or within a certain range of your foot length. And we don't have to sit there and count post-it notes. Instead, we can look at areas. And so that's the key to a density curve. First of all, the area under the curve is 1 because it represents sort of all the observations, or 100% of the observations, or so we call that area under it 1. It's always above or on the axis. It never goes below. It's almost asymptotic sometimes and gets closer and closer, like it does for a normal curve. All right, here's an example of a density curve. It's this, it's the simplest of all. It's just this horizontal line up here. It is this distribution would be considered a uniform distribution. So the example is accidents on a level 5-mile bike path occur uniformly along the length of the path. So everyone, you're equally likely to have an accident anywhere along that path. The figure at the right displays the density curve for this uniform distribution of accidents. Okay, explain how this curve, number 1, explain how this curve satisfies the 2 requirements for a density curve. Well, the area underneath it is 1, and that's the case here because you can see the height is 0.2 or 1/5, and the length is 5. So that gives us an area that's exactly 1, and the thing is above, so that's good too. All right, so the area is 1, and the curve is above the axis in this case. All right, what percent of the accidents would occur between mile 3 and mile 4? So visually, we can shade this region up here. That's what we're talking about. And then it's really just a calculation of the area. So it's the width, which is 1, and the height, which is 1/5, so 0.5 or 0.2 or 20%. All right, the next one. Betty's property adjoins the path between the 1.7 and 2.2 mile marks. What proportion of accidents occur next to her property? All right, so we could shade in her region, something like this. Again, the width is simply 2.2 minus 1.7. That's her width, so 0.5. And then the height of that area is 1/5, and so it's 10%. So we would expect 10% of the accidents to occur adjacent to her property. All right, so let's go back and let's start talking about a normal curve now. If we looked at a larger and larger set of samples, so we have I don't know how many observations I had in my foot length, probably 150, something like that, maybe 200. Over the course of 2 years, I'd probably have about 200 students. But if we took more and more and more, and maybe even plotted them more precisely, so instead of to the nearest 1/10 of a centimeter, I said to the nearest 100th of a centimeter, right? So then you would sort of get this, instead of this jagged sort of curve density distribution that we have, we would instead have a little bit more curved, and it would look a little bit more continuous. And we expect things like foot lengths to follow a normal distribution. There's certain things in nature, certain things in science, certain things in manufacturing that tend to follow a normal distribution. So normal distribution, let's talk about what the properties are. It has a maximum at the mean, so the mean being in the middle. So the maximum here is always above the mean. And truly, the mean, the median are the same thing. They're both in the middle. Since this is symmetrical, the mean and the median are going to be located in the middle there. But instead of calling it the median, we'll talk about the mean, because we also talk about how spread out this is in terms of standard deviation. So if you remember when we talked about quantitative numerical summaries, if we use mean, we always use standard deviation. And so this mu, again, this is indicating that we are talking about a population. Standard deviation with a sigma instead of an S indicates that we're talking about a population in that case. All right, so it's bell-shaped, right? It has this sort of bell-shaped here, sort of tangential or asymptotic at the ends there. It is completely described. So if I tell you what the mean is and I tell you what the standard deviation is, that's all you need to know. It tells you where it's located, the mean, and how spread out it is. That's the standard deviation. Okay. The standard deviation controls the spread. That's the sigma. The rule, the 68, 95, 99.7 rule, the empirical rule, is useful to start with, but we'll quickly get away from that. That tends to be an estimate. It's not exactly precise. So we'll use that a couple times here, and then in the next chapters, we'll get into a little bit more precise estimate. We won't use estimates. We'll use more accurate calculations. And then the last thing, 7, the change in curvature occurs at 1 standard deviation. So, for example, if you see this curve here, if you've taken calculus, you've heard something about the point of inflection, where this curve is concave down and this part of the curve is concaved up. And so where that switches over from being concave down to being concaved up is called the point of inflection. And in a normal curve, that point of inflection always, by coincidence, it just happens this way, is exactly 1 standard deviation away. So if you draw a normal curve, and the first couple times it's going to be really hard to get one that looks good. When you draw a normal curve, you can kind of estimate where the first standard deviation is by looking for that point of inflection. All right, these density curves can have shapes as well. So the first curve is a normal curve. It's also symmetrical. Not all symmetrical curves are necessarily normal. Not all bell-shaped curves are necessarily normal, but they're certainly symmetrical. All right, and then the second one there is positively skewed. It's skewed to the right is another way of saying that. All right, so remember the tail tells you the skew. So skewed to the right or positive skew means it's in the positive direction. And then the last one is negatively skewed or skewed to the left. Remember, again, the tail is going in the negative direction on a number line, so we call that negative skew or skew to the left. All right, so if we take larger and larger samples, you can see by this sort of demonstration that it gets to be a little bit more closely normally distributed. So if you look back at the histogram of our foot length, it didn't look particularly normal. It was symmetrical. It looked approximately normal, but it was not this sort of nice smooth curve that we're going to approximate it at. Okay, so what kinds of things tend to be normally distributed? Test scores on the SAT tend to be normally distributed. Lengths of newborn babies, the volume of the fluid in Pepsi bottles. The machine fills it, and it's supposed to put 16 ounces in, but it doesn't always get exactly 16 ounces. So some bottles are a little high, some bottles are a little low. We want to minimize that variation, otherwise people get mad when they go to buy a soda and there's not much soda in it, right? They can see noticeably less soda in their bottle and they get upset. So you try as a manufacturer to minimize the variation in that, but there's always some amount of variation. Things like the length of the life of batteries, cholesterol levels, the number of heads in a set number of tosses tends to be normally distributed. Okay. So it shows up a lot in a lot of different real world examples. Not every distribution is going to be normal. Some tend to be definitely skewed. All right, so we talk about what happens when the standard deviation gets small or large. So you notice that this blue normal curve is very tall and is less spread out. Remember, each one of these has to have an area underneath it of 1. So if you have a lower spread, then the height of your normal curve has got to go somewhere, so it goes up. If the spread gets wider, right, the area is always 1, so the height's got to get lower. So you can see that the green curve is more spread out. The normal green normal curve, it has a larger variation, so it has a lower height at the peak. So the smallest standard deviation is clearly the blue normal curve, and the largest is the green because it is the widest. All right, so like I said, not every set of data is typically normally distributed. And this is an example, household incomes. So household incomes are very rarely normally distributed. And it makes sense if you think about it, because there's this artificial boundary on the left, right? Nobody can make less than 0 money. So some households make little money. Some might, if you're very poor, you might make no money, right? And so you can't make less than $0. So there's an artificial boundary on the left-hand side. And then there's actually an anomaly here. This is really not what this graph looks like. These 2 bars at the end, you can't see it because it's too small down here, but they cheated and changed the width of the bar. In other words, the range of values. So this graph would continue way down past the side of this slide. So in order to get all the data to fit, they just kind of crunched those up. So ignore that. That's sort of just a funny way that they looked at bunching all the data onto one graph. Otherwise, this graph sort of goes on forever. Okay, so you have a couple people who make a lot of money, but the majority of the people don't make that much, and they're down in this range here. Okay, now it's an interesting, right? Even though this data is not normally distributed, there's no way it can be. It's always, household incomes are always skewed, right? If I take a sample from this, so if I took a sample, let's say 100 households, I randomly chose 100 households, asked them what their household incomes were, and took that data and averaged it and got an X bar, an average, a mean of 100 households. And I plot that. And then I go and do it again. And I plot that, and I do it again. I get another 100. I randomly select another 100, and I keep doing this again and again and again. And this is sort of abstract, and you're like, well, why would you do all these things? But it's a theoretical thing, and we'll see this more in chapter 7. But if I take a large enough sample and enough of them, the distribution of all the means of all the samples that I could take would itself be normally distributed. So even data that is not normally distributed, as this household income data is not, we still will be able to use normal curves in talking about the probability of selecting so many households and having their income be above or below a certain value. So normal curves are extremely useful. We'll really get into them more again in chapter 7 and beyond. Okay, so in this slide, we're going back to this normal curve and using the empirical rule. So remember that the empirical rule tells us that we are that 68%, so that's 68 means that we're 68% of the observations are within 1 standard deviation from the mean. So that means from here to here, we have 68%. And so we could fill in the percentages, like in this region right here, what percent goes in there? 34%. Now I'm writing it as 0.34. You could write it as 34%. You would just be consistent, and whether you write it as a decimal or a percent doesn't matter. All right, and so now the next number, 95, that tells us that we are plus or minus 2 standard deviations. We should have 95. Well, we've already used up 68 here, so think about how much is here and how much is here. And of course, it's symmetrical, so they're going to both be the same. So about 13.5% for each of those. And remember that the empirical rule is an estimate, it's a rule of thumb. It's not super precise, and we're going to get away from this and do more precise calculations using something called the z-score in later chapters. But for now, this works. Okay. All right, and then the last one is plus or minus 3 standard deviations. Well, that's the 99.7. We don't want to round that to 100. It's close to 100%. We don't want to round it to 100% because we know there's a little bit out here and a little bit out here. So we have to estimate this one, even though the 68 and 95, those are sort of rounded to the whole. We can't take 99.7 and round it because that would be going up to 100, and that would mean that there's nothing out here, and that's not the case. There is a little bit out there. So figure out what would be this little region in here, and of course it's the same as this little region out here. All right, and so that is 2.35%, or as a decimal, 0.0235. Okay, and then the last little bit out here, it's very small. You might have to write kind of small to fit it on your notes. So figure out what those are. All right, and so that's 0.0015 or 0.15%. So be careful. Like I said, be consistent with whether you do it as a decimal or as a percent. All right, so the first thing you want to do when you get a problem dealing with this stuff is put in your percentages into the different areas, but also put down these numbers, right? They'll give us a mean, and they'll tell us what the standard deviation is. So take that number, add the standard deviation to it to get this number, add another one to get this number, add another one to get this number, and then subtract them so that you know what these exact values are. Those will correspond, at least at the beginning, to the questions that they're asking, will correspond to those actual numbers. What percent is above it, what percent is below it, and so on. Okay, so what percent of the values lie below the mean? So remember that the mean is here in the middle. This is symmetrical, so clearly it should be 50% or below. And then likewise, because it's symmetrical, what percent is above the mean? And that's also 50%. So 50% above, 50% below. All right, so what percent lies within one standard deviation of the mean? So that would be plus or minus 1 standard deviation. Well, we can simply add these up or just use our empirical rule, right? Okay, so 68 plus or minus 2 standard deviations is the next one. That's going to be 95. Plus or minus 3 standard deviations. That would be from here all the way to there, and that's 99.7. Now, you could have added all these up, but we could really just use the empirical rule to answer those simple questions, all right? So those were all related really to the empirical rule. Now, the next 3, you really need to look at the shaded regions under the normal curve. So the first one says, what percent of the values lie below one standard deviation, above 1 standard deviation below. So what are we talking about here? Above 1 standard deviation below looks like all that, right? So what percent is to the right of negative 1 standard deviation below the mean? And so calculate that. All right, and so if you add up all those little pieces, in this case, actually, you could just do, well, we're talking about the top half of the data plus this region here. So I simply just added 0.5 to 0.34 and got 84%. All right, next one. Below 2 standard deviations above the mean. So what's that look like? That looks like something like that. All right, so below that, calculate that one. All right, and so that one's everything but this region up here. So we could take 1 and subtract these from it. We could take 50%, which is the bottom half, and add these 2 regions to it. So a couple different ways you could calculate this, but it should be 97.5% or 0.975. Again, you can either write them as decimals or percents. All right, the last one. What percent of the values lie below 2 standard deviations below the mean? All right, so that should look something like this. And we can simply add up those 2 regions, get 2.5%. So pretty small number of observations, percent of observations, 0.025 or 2.5%. Okay, so your homework for this part of chapter 2 is not out of your textbook. There is a homework sheet that I gave out in class. If you weren't in class, then look for this, the PDF of this, in the same Google Classroom post as this video. And it is due next class.